So I will be starting soon. Those who join me can text me. If you guys want to text me, you can text me. I will start after 4 minutes. And if you don't hear or something, do you guys hear me? If you hear me and you see the presentation, just say anything or text me in anything anyway. Do you guys hear me? Those who are viewing, do you hear me? You can WhatsApp me, you can write here on YouTube, whatever you like. Can you write to me on YouTube? Can you comment? Rabah, do you hear me? Great, so I will start in 2 minutes. Just waiting more people to join. So far we have 4 viewers, not too bad for the first time. I will start in 1 minute. Okay, great. 1 more minute. Hope more people will join us. We still have only 4 viewers. Great. We have Rabah, Shema, we have Dana. And yes, that's all. We have 4 people joining us. Let's see how many will join us. Some of them will have internet problem, I'm sure. So after each slide, I will check if any question. So I'm going to start. As you guys know, my name is Yahya Ithawi, and I am a consultant neonatologist. So depending on the request of many colleagues, today I will be talking about the neonatal ventilation. And my objectives is to talk about the initial setting and then the lung recruitment and the best PEEP, maintaining ventilation and patient ventilator asynchrony and troubleshooting, what we will do with abnormal gas and how we wean, and if there is any complication and how we extubate. Habibi Dr. Khalid, thank you very much for joining. انت استاذنا يعني I don't know, well, this is very simple talk, so I don't know if you are really want to hear this. It will be very simple talk, so probably you know more than me, but these are very principal for those colleagues who asked me to do so. And please feel free to ask any question and also to correct me if I say anything probably wrong or inappropriate. When we talk about the initial ventilator setting, we need to select the type of the ventilation, whether pressure and volume. Most of neonatal care we use pressure limited ventilation, and after that we have to decide about the mode. And then when we look at the ventilator, we have a set parameter and a measured parameter, and these setting for any ventilator to work are the PEEP, PIT, rate, inspiratory time, tidal volume, trigger variables, control variables, and phase variables. Now, to recruit lung, we need to expand alveoli. Now, all people ask me, what is the best PEEP? Now, there is no evidence what is best PEEP, but we know that each patient will require a different PEEP. And the PEEP is the pressure needed to maintain the alveoli open during exhalation. And therefore, I always say there should be dynamic PEEP. And the people should avoid the PEEPophobia. I'm a person who's very PEEPophilic. I love PEEP and I usually give high PEEP when it's needed. And I would use low PEEP when needed. So always I would say use dynamic PEEP. So increase the PEEP as needed, recruit lung, and then decrease PEEP to maintain the oxygenation. And by doing so, or giving dynamic PEEP or PEEP only appropriate for what is the appropriate for that particular baby, I call it dynamic PEEP. And the benefit of using dynamic PEEP or appropriate PEEP is optimizing lung recruitment, which means you're opening all alveoli, which means that you will use enough alveolar bed to appropriately fit the pulmonary vasculature bed, and therefore you prevent the intrapulmonary shunt, because if the alveolar bed less than the pulmonary vascular bed, there is some part of the pulmonary vascular bed will not be in contact with oxygenation, and therefore it moves from the artery to vein unoxygenated, and that's called intrapulmonary shunt. When you use appropriate PEEP, also you improve lung compliance, because imagine you have two balloons. One is brand new and one is old. When you're trying to inflate both of them together at the same time, the old will inflate easier than the old and than the new. And therefore, using appropriate PEEP will keep the alveoli as an old balloon, and it's easy to be inflated using the PIP. And therefore, when you use optimal PEEP, you will need less PIP and therefore less damage. And then we'll be talk about the opening and closing alveoli. Using appropriate PEEP will prevent that, and I will show you in the next few slides. Appropriate PEEP also will be good to recruit diseases that cause secondary lung atelectasis. prevent child exhaustion, improve oxygenation, and improve all the respiratory parameters. So I will move to the first part of the ventilation, which is the PEEP. The PEEP, as I said, is the pressure needed to maintain the alveoli open between the breaths. The PEEP, which is around 3 to 4, is considered physiological. However, the PEEP we apply should be above that physiological, because we have a dead space and we ventilate not a physiological lung, we ventilate a sick lung. And always remember that the lung compliance improves, and it's documented by evidence that improvement in lung compliance when we use PEEP more than 5. And as you can see here, there is a pressure and there is a time, and that's what we call it graphics. So you can see that there is basic pressure, which is the pressure above the zero. And for the ventilator, the zero is the atmospheric pressure. So any pressure applied to the lung above zero called PEEP if it's applied through a whole respiratory cycle. But between the respiratory cycle, during inhalation, there is another pressure which called the PEEP, or positive inspiratory pressure. So we have PEEP and we have PEEP. Now, what is the best PEEP? Is the PEEP that improve the functional residual capacity. And you can see here in this graph that with increasing PEEP, the alveolar diameter is increasing until we reach a point up to 15. When we increase the PEEP more than 15, there will be no increment in the alveolar volume. And therefore, the PEEP should be, as we said previously, above 5, below 15. So usually the standard PEEP from 5 to 15. You should never use above 15, because you will get stretching without improvement in the contact between the alveolar bed and the pulmonary vasculature bed. And below PEEP is you're getting away from the opening pressure that we will talk soon about. So I'm going to pause here to see if there is any questions. Okay, there is no question, so I'm going to continue. I always said to my colleagues that there is confusion between CPAP and PEEP, because most people will talk about something called CPAP, and then they said CPAP will have PEEP of 6. So remember, CPAP is not PEEP. PEEP is the pressure need to keep alveoli open during expiration, while CPAP is the pressure that's applied to the nose above atmospheric pressure. Some of that CPAP will be PEEP and some will be leaking. So remember, CPAP is not PEEP. So when we say CPAP, you can say CPAP centimeter, 6 centimeter water. You can say CPAP of 6 of PEEP of 6 centimeter. Remember that PEEP is not CPAP. So you can see, as we say, the ventilator considered the atmospheric pressure as 0. So any pressure applied to the lung above 0 during the whole respiratory cycle is the PEEP. Then there is a pressure applied during inspiration. So the pressure usually starts increasing suddenly, and then decrease, and that's what we call it the rising time, until we reach to the peak of inspiration. And then there is sudden drop of the pressure, and that's what and then after that sudden we start what we call it the plateau pressure. And you imagine when the air comes into the alveoli, it starts with the airway until it reaches the alveoli. So the beginning and the end of the inhalation represent the beginning of the inhalation or movement or inflow during inspiration represent the airways, and the end of the inflation represent the compliance of the alveoli. So we have the rising pressure, we have the peak or Pmax, and then we have the airway resistance, and then we have the plateau until we reach the alveolar resistance, and we're going back to the PEEP. Now, what is the advantage of good PEEP? As we said, you expand the lung. So, and then that expansion should match the pulmonary vasculature bed. If it's more, that's over distension. If it's less, then you will have intrapulmonary shunt. So the optimal PEEP or dynamic PEEP or the PEEP appropriate for that baby will be exactly matching to the vascular pulmonary bed, and that's very difficult to achieve sometimes. And by doing that, we'll decrease shunt. Once we decrease shunt, but we don't cause over distension, so we have alveolar bed, pulmonary bed. They should match. If the pulmonary bed is more than alveolar bed, then we have the intrapulmonary shunt. If the alveolar bed more than pulmonary bed, then we have over distension. So using good PEEP will prevent shunt. The other one, it will increase compliance. How? Because it will keep the alveoli open. And I will go back to my examples. When I use two balloons, they are connecting together and I am inflating them at the same time. The old one will be inflated easily than the new one. And imagine the old one is the open alveoli and the new one is the collapsed alveoli. So having a good PEEP will keep the alveoli as an old balloon, and it's easily to be opened by the PIP, and therefore we have improvement in compliance and decreased work of breathing. There are many types of PEEP. The PEEP that we applied through ventilator, which is and then the PEEP that is created not by the pressure of the that we apply through whole respiratory cycle, but by inappropriate setting. And then we have the total PEEP, or the PEEP that is causing the expansion of the lung. So what is the auto PEEP? So imagine this is this line here. Imagine that this line, the dotted colored line, is the normal. And imagine this is another line because of inappropriate setting. And you can see that inhalation here started before the previous exhalation reached to the PEEP. So this exhalation should goes back to here and then goes back. Sometimes because we use a bad setting, the next inhalation starts before the line goes back to the PEEP, and therefore the difference between the starting of improper ventilation above the PEEP called auto PEEP, and that causes air trapping. And you can see here when we look at the flow, we can see that we have inflation and then we start deflation, and this flow graphics are very important. It's almost the best thing that to monitor the ventilator, and you can see that the exhalation starts before this flow goes to zero. So the baby starts to inspirate, and then the ventilator will give the exhalation. And you can see that next inhalation also starts before the exhalation starts to zero, and that's causes the air trapping or the auto PEEP. So I'm going to break here to see if there is any question. No more questions. So I'm going to continue. Now we will talk about the PEEP, which is the pressure applied only during inspiration. So we have PEEP, which is applied through whole respiratory cycle to keep the alveoli open during exhalation, and then we have the PEEP, or positive inspiratory pressure, which is the pressure applied only during expiratory cycle. Both of them are above atmospheric pressure. Although the atmospheric pressure is 760 centimeter water, but for the ventilator, the atmospheric pressure considered to be zero. Now the PEEP on the graphics are actually not of two types, they are actually of three types: the spontaneous, the mandatory, and the assisted. The spontaneous is mostly will be either spontaneous without help of the ventilator, but sometimes with the help of the ventilator. So I'm considering them both are spontaneous. So you have the spontaneous done with the baby without the help of the machine. We have the assisted, started by the baby, which we call it trigger, we'll talk about, and then continue by the ventilator. And they have the mandatory, which is delivered only by the machine. The other, so we talked about PEEP, and now which is the most important parameter to set, and then we talk about frequency. Now the respiratory rate, usually both the spontaneous, mandatory, and assisted ranges between 10 to 60 breaths per minute. Rarely we go up more than that, but sometimes I use more than 60 up to 80, because remember, there is something called minute ventilation, and in pediatrics or in neonates specifically, the minute ventilation depends more on the rate than the tidal volume. So increasing the rate is a great tool to ventilate a baby. So when we say mandatory, or the one delivered by the machine, is the backup rate. And also we have the assisted, which is started by the baby and then held by the machine. So we have three breath types on the graphics: is spontaneous, mandatory, and assisted. The other parameter that we should set in addition to the rate, PEEP and PIP, is the inspiratory time. And the inspiratory time is the length of inhalation, the length of the breath, how long this baby should. And the inspiratory time, usually we set it in a time cycle ventilator. And what is mean time cycle? The cycle means when the ventilator will change from inspiration to expiration, from phase to phase. So if that ventilator, some of the ventilator use the flow to cycle, but most of the ventilator use the time to cycle. So in this situation, we are telling this ventilator that when you start the inhalation, give inhalation within 2.2 to 2.3 seconds, and then after that stop. There should be pause before the exhalation starts. Now the inspiratory time, I don't like to have a number. I think the inspiratory time should be set depending on the graphics. And again, we have three graphics, which is the volume, the pressure, and the flow. And in my practice, I think the sole graphics that we should look is the flow. Although there is a normal, not a normal, but acceptable inspiratory time, however, which is range between 0.2 to 0.6, but I don't like it. When we use the flow to cycle the ventilator or change between the phases of ventilation, which is inhalation, expiration, and the pauses in between them, we depend on the flow. Once we use the flow, then the inspiratory time varies, because it can be high, it can be low, to achieve the desired flow. Because we will tell the ventilator when we have 0.1, then give inspirations. When we reach to that flow, stop, and when you reach to 0, start expiration. And therefore that might change depending on the patient and the ventilator variables. When we set the inspiratory time, because we have a respiratory cycle, the respiratory cycle is composed of three parameters: the inspiratory time, the expiratory time, and the rate. Because remember, the ventilators deliver the ventilation over 1 minute. And these three variables, the inspiratory time, the expiratory time, and the rate, when we set two of them, the other one, the third one, will be default. So for example, if you said the rate is 50 or the rate is 60, which means 1 cycle per 1 second, and the inspiratory time is 0.3, then the expiratory time will be 0.7. If we say the inspiratory time 0.2 and the expiratory time is 0.8, then by default the respiratory rate will be 60. So it's very important to remember that. So there is a relation between inspiration and expiration. So you can see here, this is a flow, there's very sharp rise, and then there is no flow, and then very sharp decrease, and there is 0 between inspiration and expiration. Expiration starts all of a sudden and then goes back, and you can see here there is air trapping because we are not giving time for expiration, and the next inspiration start. We should always, when you look at the graphic, there should be pause between inspiration and expiration and next inspiration. And that would be the best ventilation. You can see here went to 0 and here went to 0 because we have a very good expiratory time, because you can see here we have inspiration, 1 expiration, inspiration, we have 3 expiration, and you can see that the baby went back to 0 before next inspiration. So it's very important when we determine the rate, we look to the graphics and change the rate, inspiration and expiration, these 3 parameters depending on the graphics. I hate giving and I don't like giving number. I'm going to pause here and see if there is any question. Oh, there is a question here, is what do you mean by decreasing shunt? So imagine you have 2 balloons, okay? One is red and one is blue. And imagine the red balloon is the alveolar bed and the blue balloon is the pulmonary bed. What you want, we want the size of these 2 balloons together the same. So the red and blue balloon are the same. When you contact them, they have exactly matching. That would be the best you want. However, if the red balloon, which represents the alveoli, is larger than the blue, which is represent the pulmonary vasculature, you're getting over distended, you're stretching the alveoli, but that increment over the red balloon is not used. So you're using over distension, but you're actually not contacting the pulmonary. That's called over distension. Imagine that, however, the blue balloon, which is represent the pulmonary vasculature, is bigger than the red balloon, which represent the alveoli. And in that case, the one of the or part of the red balloon, which is not in contact. And remember, that balloon get the blood from the artery and then give to the vein. And therefore, some of that blue balloon is sending the blood back to the vein without contacting the alveoli. And that's, we call it intrapulmonary shunt. So what do you want? You want the red balloon to match the blue balloon. You don't want the pulmonary vasculature to be bigger, and that's intrapulmonary shunt, and you don't want the alveoli to be bigger, and that's what we call it over distension. I don't know if I answered your question. Is that clear? So, and then if you have more question, I can continue explaining what exactly I mean by the now inverse IE ratio. Always the inspiratory time is way better than smaller than expiratory time most of the time, and sometimes we have certain indication to use inverse. I don't suggest that you use it right now, and that's why I will skip it, but I can explain it if somebody wants. But I don't advise that we use reverse IE ratio. And remember, the best IE ratio is 1 inspiration to 2 expiration to 3. So if you are using 0.3, then the best expiratory time is ranging between 0.6 to 0.9. And then by that, the rate will be default. So that would be best. So if I put inspiration at 0.4, the best expiratory time will be 0.8 to 1.2 seconds. And then you get the rate. That would be your best goal. In reverse, instead of you get other way around, so you get, let's say, 0.3 of expiration, 0.3 second, and 0.9 of inspiration. I don't advise it, but there is certain indication that you can use inverse IE ratio. Now, what is the mean airway pressure? Some people call it MAP, but that's not a preferred term because it's confused with the mean arterial pressure. So people use it as PAL, or the positive airway pressure. And it represents the entire pressure during one cycle. Represent the PIP, the PEEP, and also represent the inspiratory cycle. And because inspiratory cycle affected by inspiratory time, then this mean airway pressure affected by all these parameters. And some people call it the area under the curve, and I will talk about it. The best MAB would be in neonatology between 10 to 15 centimeter water. And remember that the risk of pneumothorax and pulmonary airway interstitial emphysema have risk. And when we talked about MAB of high frequency, this is totally different. So I'm not going to talk about MAB of high frequency. I'm going to concentrate on our conventional mechanical ventilation. Now, the most important, remember, in neonatology is not the tidal volume and it's not the rate. It's the min ventilation. Because you can give tidal volume of 6 or 6.5 or even 7 or 8, but you won't achieve a good volume as the rate, because remember, tidal volume is important in adult because we have low respiratory rate, but in pediatric or in neonate especially, we have very high respiratory rate. And remember, you don't depend only on tidal volume, remember your rate, because the optimal goal is your minute ventilation, which is the amount of, or the mils of air that going per kg per minute. And remember, always to remember that, and usually range between 150 to 300 mil per kg per minute. It's very important to remember that, because we don't depend only on tidal volume. Remember to look, when you look at your ventilators and you have high CO2, to look to your minute ventilation, which it's the rate times the tidal volume. The tidal volume is amount of the volume going in one cycle. Okay? And always remember that both volume and pressure is related to time. So the speed of the flow is the pressure, and the time of the flow is the volume. And remember that when we talk about tidal volume, we measure it in mil, and it can be in liter, and you always prefer it to be per kg. And remember, the volume is the flow versus time. So the longer the time, then the better the volume. But the faster the flow, the better the pressure. And that's very important to remember. In short, the tidal volume is the size of the breath. And in both volume limited and pressure limited, or in VG, this tidal volume need to be either set or looked at. Because remember, we have two parameters in the ventilator, the one we set and the one measured by the ventilator. Now the type of the tidal volume determine the type, depend on the type of breath. Again, I'm saying here two, but what I mean is mandatory and spontaneous, and by spontaneous I mean spontaneous and the one also achieved, assisted by the machine. So it's better to say that there is three types of breaths: mandatory, spontaneous, and assisted. The other way of looking at the ventilator is the loops. And the loops give you the dynamic of one cycle. So I don't much prefer it, because the graphics give you one parameter versus time and give you, an idea about ventilation over a long period of time. But also you can use the loops, and the loops give you the dynamic of one cycle, and it's compared to parameters. So you can see here we are comparing the pressure with the volume, and you can see that we are starting from 0, and then we are inflating, so we're increasing pressure, but actually we're not getting any volume until we reach a magic point called opening point, where a minimum increase of the pressure gives you lots of volume. Until we reach to a point, then we'll get more pressure, but actually we're not getting any volume, and that's what we call it over distension. So here we call it, in this area, we call it under distension or collapse, and here we call it over distension. What does that mean? You get pressure, but you don't get volume. And here also you get pressure, but you don't get volume. And then you have the expiration, and then you reach a magic point where we call it closing point. So you need the pressure or the ventilation to be in this area, or what we call it the safe. You can see here that we get a pressure, we are not getting volume, and then oops, all of a sudden we get a good volume until we reach. But we are here, we're stopping, we're not giving. So this is our distension, this is under distension. And remember, here we have the PEEP, because here there is PEEP, but also we have, is not demonstrated, I will show it to you later. But remember that with good PEEP, you will get this time from starting the PIP till you're reaching the opening point is shorter, and therefore good PEEP is important. So I'm going to stop here and see if there is any questions. Any question? If there is any question, please ask me. If there is any problem, also tell me, because I'm going to continue. This is another way of loops, or looking at the dynamics of one breath. We're comparing here the flow to the volume. Okay, so you can see that this patient is breathing in, breathing in, breathing in until he reaches peaks and then goes back. And this area, so you can see the flow and this volume. So he is breathing in, stop, then decrease breathing in until he goes back to zero. And from this area to this area is our volume. And then he starts to breathe out, and then goes back to zero. So this gives me how much flow to give me the dynamic of the volume. And you can see here that this patient have a flattened inspiratory flow. Okay, so you can see with minimal flow, I'm not achieving any volume during inspirations, and then I reach expiration, and then I have zero volume. And that's what we call it scoop out expiratory flow, and that's how when you have air trapping, and therefore you have reduced expiratory flow, and that's what we call it a flattening inspiratory flow, a flattening expiratory flow. Another dynamics, you can see that you have very high flow, but you're achieving very small volume. That's a steeping end inspiratory flow curve, and that's when you have low tidal volume. The time constant, nobody used it, nobody think about it, but the time constant is the multiplication of compliance and resistance, and it is usually the time needed to inflate up to about 75% of the, or 95% of the alveolar bed. And usually it is equal to 3 times inspiratory time. I don't want to talk about it much because I don't think it's so the graphics here, as we said, rate the give you the view about the whole inspiration over a long period of time, while the loops, and it compare one pressure parameter versus time, while the loops compare one parameter versus one parameter and give you the dynamic of one cycle. And so when we look at the pressure, you can see we have the PEEP, and we have the PAB, and we have the PIP. And you can see the MAB is the under all. So it represents the PEEP, the MAB, the respiratory rate, the inspiratory time, the expiratory time, all be affected. And when you look at the end, you have different type of shape, depend on different mode of ventilation. So you can see a triangular shape of pressure when the slow rising time and then slow decreasing time. But you can have rectangular when you have sharp increasing time, then you have a plateau, and then sharp decreasing time, and then we have sinusoidal when you have, so you can see here is volume limited, you can see here is pressure limited, and you can see here hybrid type of ventilation. And again, the MAB is represent actually everything, represent the frequency or the rate, represent the inspiratory time, represent in 1 minute, represent the PEEP and the PIP. The graphics of the flow a little bit different. So we have positive in and negative out, and then we have different type of shapes. We have what we call a descending ramp, we have square, we have exponential decay, we have sinusoidal and descending ramp. Now each one has a representation of something, but I'm not going to talk about it because I don't want to complicate things. We have the volume graphics, and there are also different type of shapes, and we have usually we see all of them together. And for me, the most important is the flow. So I'm not going to talk about the graphics because the lecture is not about graphics. So the phase of respiratory cycle is we have pause before inspiration, and then we have the inspiration, and then we have the rising inspiratory rise, and then we have the inspiratory phase, and then we have the expiratory time. The type of the breath, mandatory, assisted, and spontaneous, and you can see it in the graphic, each one is different, so I'm going to pass this. And then in the ventilator, we have two types. We have synchronized ventilation. Turn off the light. We have synchronized ventilation and we have asynchronized ventilation. And the synchronized ventilation means that the ventilator will never give a breath without when the baby try to breathe. So there will be usually time for backup rate for apnea if the baby is not breathing. So the backup rate, for example, if it's 30, then the ventilator will wait 2 seconds before giving the breath, looking for. But when the baby breathe, the ventilator will synchronize when. So you can see this is synchronized breathing. You can see that this is spontaneous, not supported, and you can see this is a spontaneous, not supported, and you can see this is asynchronized. So there the ventilator is trying to breathe and the baby is trying to breathe. You can see the flow. There's two flows: the ventilator and then the baby. So you can see synchronized, asynchronized, and spontaneous, unsupported. The trigger is, there are different types. It can be flow, it can be pressure, it can be neural or naval. The most important is the pressure, which means that when the baby breathes in, let's say by 0.2 liter per minute, then we will tell the ventilator, when the baby does that, give him or give her the breath. If you set it 0.5 liter per minute, so the ventilator will not trigger or assist the breath until the baby reach 0.5. So the higher the number, then you make it difficult for the baby. So if you want your baby rest or you're not planning to extubate, then usually go with low trigger. If you want to train the diaphragm and train the baby, usually you would go with high trigger. But it also can be flow, which means when the flow is negative, the trigger. So here's how the ventilator think, or you can see in this, there is in and there is out. There is in and there is out. And the baby, so the ventilator gives in and the ventilator goes out. When they are equal, mean there is no effort from the baby. When there is the in is not equal the out, now the ventilator will trigger. And that's how the ventilator sends the trigger. So you can see that there is no trigger, but here you can see there is a trigger. You can see there is a trigger. You can see also the baby breathe in, breathe a little bit, trying to breathe, and then the ventilator will give some, because it gives some negative pressure. The variables are of the ventilator are pressure, volume, and flow. I'm going to pause this. I don't want to go. I'm going to pause this. The mode of the ventilation. Now, this is very important slide. It tells you about the mode of the ventilation. So you can see the white part of the picture is the patient part of the contribution to ventilation, and the white is the machine or the ventilator contribution. And you can see at CPAP, okay, neither the patient nor the machine providing anything other than PEEP. But when you start to give something called pressure support ventilation, mostly are controlled by the patient, a little bit by the machine. when we get IMV, which is non-synchronized intermittent mandatory ventilation, more by the machine. SIMV, more than the machine IMV. I think this is, I meant PTV, and you can see PTV or assisted control or SIPBV, all are added by the machine until you have conventional mechanical ventilation, which is mostly controlled by the machine. Now this is again a description and a difference between different mode of ventilation, which I will speak about. So what is conventional mechanical ventilation? The conventional mechanical, nothing more than giving PIP over the PEEP in a certain number, and it's not synchronized with the patient, and therefore it's only used when you have complete paralysis and you have heavy sedation or coma. So you patient actually in conventional or mechanical ventilation, you are not contributing to anything, or some people call it SIMV. It's not contributing to anything. So you set the rate, you set the PIP, the PEEP, the inspiratory time, and if the patient tries to breathe, it will not be supported. And this is the graphic, so I'm going to pass it because there is no time. And the assisted control, or some people call it SIPPV, or some people call it PTV. The ventilator have two types of breath. Because in SIMV there was no support to patients spontaneously. Only what the machine is delivering is what you set. In assisted control, however, same as IPPV or same PTV, there is the PACA break, which is the rate will be delivered by the machine. But if the baby try to breathe within the trigger limit, over that rate, the machine will help. So let's say if you set the rate to 30 and the baby breath 50, then the machine will give 50. While in SIMV or the CMV, if you set 30, the machine will only give 30, and so on. So I'm going to pass this because there is no time. IMV is same exactly of CMV. There is no difference. It's not synchronized with the patient, and it's only delivered the PEEP, PIP, inspiratory time that's set by the operator. The SIMV or the synchronized CMV is the same of SIMV. It's only delivered what you set. It will not deliver the extra. However, in SIMV, different from IMV, it's synchronized with so it will never breathe or deliver breath over the patient. And this is the graphic of SIMV. I'm going to pass it. So comparison between SIMV and assisted control. All of them is the same. The difference is that when in assisted control, if you set the rate to a backup rate that would be delivered by the machine if there is apnea or the baby is not breathing. But if the baby breathes above that, a machine will deliver. So let's say you set the rate to 30 and the baby breathes 60, it will deliver 60. If you set the rate to 30 and baby breathes 40, it will deliver 40. In SIMV, if you set the rate to 30 and the baby breathes 40, it will only give 30, and so on. So let me pause here and see if there is any question. Do you guys hear me? Any comment? Do you guys hear me? Any comment? If there is any comment, any question? Okay, well, let me continue then. The PSV is the difference that the patient will control the inspiratory time. So instead of determining the inspiratory time, you give a long expiratory time, and the baby can breathe within that inspiratory time. It's exactly same with the SIPPV, but the difference that the patient will control the inspiratory time. So I'm going to pause the graphics, and this summary of all the mode of ventilation. And you can pause and look at it and what exactly it tells you. And sometimes you use a combined ventilation, for example, ACVG, which is assisted control plus VG, or SIPPV plus VG, SIMV plus VG, PSV plus VG. Also, you might add VIVE. So the best PEEP is depend on the analysis of the flow, volume, or pressure. And then you need to maintain adequate PEEP above the closing pressure. Prevent intrapulmonary shunt to improve oxygenation, and increase intrathoracic pressure to maintain hemodynamic stability of right to left heart, of the right and the left heart. Decrease venous return when you overdistend. When you need high PEEP and you cannot drop it, and there is a little bit of hypotension, you can give boluses or use inotropes. So here, what is best PEEP? So you can see here there is inspiration. Sorry about that. So you can see that this baby is inspiring. So you can see starting from 0 and the pressure is increasing until reaching opening point where the volume is increasing. And then he reached to a point where the pressure is increasing but there is no volume. So that's what we call it opening point, and this is the maximum critical point. And then he will expirate, and you can see this what we call it peaking, and this what we call it critical closing point. So this is overdistension, this is atelectasis. You want to be here. So if you see that, if you bring the PEEP in here, you always will be in the safe time. So it's important, you have to have a good PEEP when you gap the distance between the 0 and the opening pressure. So unsafe injury, safe window. No overdistension, no underinflation. Again, you can see here there is overdistension, and you can see there is shortening of the movement of the curve of the pressure until the opening of the PIP, opening alveoli, because of good PEEP. You can see in the previous slide that there was overdistension. You can see here there is no overdistension because we are not using extra pressure. We've stopped when we are not achieving a tidal volume. You can see here is more pressure, but we're not achieving any volume. You can see the volume in here equal to here, equal to here. So you're getting overdistension, but you're not getting any volume. So you don't want to. You want to use this. And you can see if you drop the PEEP, then the distance from the 0 till opening pressure become longer. So you need to make it shorter. So the best PEEP is to titrate to see the optimal loops, titrate PEEP to get the best saturation with lowest FiO2, and that's what I call it dynamic PEEP. So if you have inadequate ventilation and you're ventilating a baby and achieving the saturation